Okay, so today we'll talk about rejection sampling. Well, let me just address a couple things. We haven't graded your midterms yet. I'm going to get together with my TA this week. I mean, we'll virtually we'll meet online and we'll try to get your exams graded this week. So so that's what we're gonna we'll do. So give us a few days for that. In the meantime, or today I'll talk about rejection sampling, and then probably on Friday we'll start to introduce concepts of Markov chains, and I'll post a homework assignment pretty soon as well that will deal with random sampling. Okay, so we've got. All right. Okay. So we introduced rejection sampling on Friday, and we'll just take another look at it. Go a little bit more in depth. I've got some like a little animation to show you that I don't know, maybe it'll be useful or helpful to illustrate. Okay. So so just kind of taking a step back and looking at the big picture. Random sampling is a method for us to generate random values from a distribution. And we want to be able to generate values from a distribution in order to do things like Monte Carlo estimation and things of that nature. All right. And, you know, R already has a bunch of built-in functions that will help, that will generate values from lots of distributions. But if it doesn't have a built-in function, then we've got to use one of our kind of variable generation techniques. And so we have, we've looked at inverse CDF, okay, and that will work. But then sometimes you might not be able to get the CDF or the inverse of the CDF. And in those cases, you would need to, you might want to consider rejection sampling, okay? I mean, in general, if you are able, okay, so this is kind of the hierarchy. If there's a built-in function in R, just use the built-in function in R, okay, in general. If there's no built-in function of R, see if you can figure out the CDF and the inverse CDF, okay? In general, the CDF and the inverse CDF are gonna, inverse CDF method is more computationally efficient in that values that get proposed, not proposed. Every uniform value, so when you generate a value from R uniform, it will get, it will become a random value of X, okay? So, so there's no inefficiency in that. You're not throwing values away. But in some cases, we can't figure out the CDF or the inverse CDF because it involves an integral or something tricky. And in that case, rejection sampling only requires that we know the PDFs, okay? If we know the PDFs, then we can do rejection sampling. And, but it's not as efficient because as the name would imply, when you do rejection sampling, some values get proposed and some values get accepted and some values get rejected. And so, so the computational energy you spend proposing values, not all of them will get used. Some will get thrown away. All right, and so the way rejection sampling works is that all you know is the PDF. You know the PDF of F, but you don't know this inverse CDF, okay? And so we're not able to use inverse CDF, and we're not able to generate directly from F. So the solution is to find a candidate distribution G of X, okay? And G of X has to be a distribution that we are able to sample from. So it could be as simple as the uniform, because we always know how to sample from the uniform. But the other requirement is that the support of X, the support of F has to be fully contained inside the support of G. So whatever distribution you're going to use to propose values, your proposal distribution, the support of f has to be contained fully inside. So if your target distribution is something like the normal distribution, or we're going to look at the folded normal distribution today, that the support of the folded normal goes from 0 to infinity. And so we can't use the uniform distribution because the uniform distribution, is on a bounded interval. Now you might say that the probability of getting something from the folded normal, anything that, the probability of proposing getting a value like greater than 10 is close to 0. And so maybe you'll just say, I'm going to propose values from the uniform distribution from 0 to 10. And that's probably good enough, because how often is a normal value greater than 10? Almost never, but so that could work. but maybe we don't want to do that as well. Okay, so anyway, you get some distribution G, and the requirement is that the support of F has to be inside the support of G. And then what we are going to do is we're going to scale G, we're going to multiply it by M, so that the density G of X times M times G of X is always going to be greater than the probability F of X, the density function F, okay? And so, you want to pick an M that is going to satisfy this criteria, but you don't want anything bigger than that, okay? If you pick a M that's any bigger than that, your scaling factor is going to be too large, and you're going to be throwing away a bunch of values. So, so the most efficient choice is going to be find the maximum value of F of X divided by G of X, okay? Anything bigger than that, it becomes inefficient. Anything smaller than that is not going to be big enough to satisfy this condition that M times G of X is greater than or equal to F of X for all X, okay? So we're going to have to find this value of M by finding the max of F of X over G of X. And here's our sampling algorithm. We're going to generate an X from G. We're going to calculate this ratio, F of X divided by M times G of X. And then to help us decide whether we accept that value or not, we generate a random value U, and we're going to compare U to this ratio. If U is less than the ratio, we're going to accept the value X that was proposed. And if U is greater than the ratio, we're going to reject X and just keep going, okay? And we're going to just we're going to end up throwing away values, any value that is greater than R of X. Okay, so what I wanted, my hope for today is to give you some pictures that will help you gain, I guess, a little bit of intuition regarding rejection sampling. I don't know, maybe it's already intuitive and you don't need any of these pictures, but that's what I want to do. Okay, so we're going to look at the PDF of the folded normal distribution, which is basically the normal distribution times 2 and only on the positive side, right? Because PDFs still have to integrate to 1, and we're only keeping the positive half of the normal density, okay? And so I'm going to take my normal density, I'm going to multiply it by 2, okay? I guess this is the folded normal of the standard normal, where we fold it at the origin. Technically, the folded normal could be offset, and then you fold it, and it's not necessarily twice this, but we're going to take the standard normal distribution, fold it at 0, and we're going to get 2 times the normal PDF. And then our candidate distribution is going to be the exponential distribution with the rate parameter equal to 1, and that's going to be e to the negative x. That's going to be our PDF, right? The PDF is lambda e to the negative lambda x, but with lambda equal to 1, it just becomes e to the negative x. And this is going to be a PDF. The support of our proposal is all positive values, and the support of our target distribution is also all positive values. So our supports are compatible with each other, or the support of G fully contains the support of F. And so if I plot this, this is what it looks like, okay? the proposal distribution shows up in orange, and the target distribution, our desired distribution, shows up in red, okay? And what we see is that there are places where the orange is greater than red and the red is greater than the orange. That in some places, the proposal distribution proposes too many values compared to what we desire. And in some places, the proposal distribution doesn't propose enough, okay, if we take it directly, right? So what so we're going to kind of have to find that scaling factor, okay? A scaling factor either to multiply by the proposal in orange, so that's always taller than red, or we multiply the red, the target, by 1 over that scaling factor, 1 over m, so that's always less than the orange. Okay? So, so here again, we're going to do a little bit of math. We're going to find that scaling factor, that constant m, so that m times g of x is always greater than f, okay? Another way you can think of it is that g of x is always greater than f divided by m, okay? So that's another way to think of it. And so that the m is, we're going to set to be the maximum value of f of x over g of x. So the entire PDF of f, the PDF of f is this, and the PDF for g is this. And we want to find, okay, well, what is the maximum value of this thing, okay? And so, you know, just with a little bit of calculus, when we look at this, we can see e is raised to this power. And so the maximum value of this is going to occur where this quantity is as small as possible. And so just solving it, you know, with a, you know, it's a parabola here. And so the minimum occurs where x equals 1. And so if we plug in x equals to 1 into the equation, we're going to get that this constant m is equal to 1.32. Right? Okay, so this is an important step, is you got to figure out what this m is. And so so we pick a value 1.32, and then so if I run that, then the algorithm will run, and everything will work. So here our scaling factor is 1.32. The f is 2 times the normal PDF, okay, and g is the exponential PDF. Okay, so I'm just using r's built-in functions here, d norm x and d exponential x, but you know, you could enter these yourself if you need to. Okay, and I generate 100,000 values, okay, from the random exponential. So the values are being generated from our proposal distribution g, that's the random exponential. And then we're going to accept them based on this ratio. And so this is vectorized, okay? I'm going to do f of the, I'm going to find the density for the proposed values of x. I've got 100,000 of these values. So here I've got a vector f, the densities of those 100,000 values. And I'm going to divide by m times g, which is a density function of these 100,000 values as well. Okay. And so this is vectorized, so this is great. You might have some PDFs that are piecewise, and so, you know, if it's piecewise, when you write your PDF, you often use an if statement, right? You'll say if x is less than 0, then it should take on this form, and if x is greater than this number, you know, it should take on this value. But if you throw an if statement into a function, that function no longer becomes vectorized, right? So if you want a vectorized function for your PDF, you'll have to get a little bit creative, and you'll probably need to use statements like if-else, okay? The if-else statement is a vectorized thing, okay? So, so what you can do is you can create a function. I'm just talking this out loud without putting anything up on the screen. But let's say you have a piecewise function, right? So let's say you have a triangular distribution where let's say from x is 0 to 2, it goes up, and from 2 to 4, it goes down, okay? So what you can do, what might be easier, is if inside your function, you just calculate all the values going up, and then you calculate another vector values where they're all going down, like this. And then you use an if-else statement, which is vectorized. And then using the if-else statement, you're going to either take the value from this side or take the value from this side, and then you'll combine them together into a vector, okay? Rather than using an if statement, if that makes sense. Because if you use an if statement in a function, that function no longer becomes vectorized. You have to feed it. You have to write a loop where you say, plug one value into the function at a time, and it spits out a value. But we like to, with R, we like to work in vectorized forms, right? So that would be my recommendation, is to make a function that's vectorized. Okay, so anyway, we're going to get the ratio. We get a vector of ratios, and then we're going to run our unif to get a whole bunch of uniform random values, and we will accept it if u is less than that ratio. Okay, and so accepted is going to become a logical vector of true falses, and we subset the proposed x's, which we have 100,000 of these. We only keep the ones where accepted is true. And so accepted x is going to be a lot smaller than proposed x. Okay, it's going to be smaller by around a factor of m. So you do 100,000 divided by 1.32. That's going to be your approximate size of accepted x. Okay, so so depending on your function, okay, if there's a big mismatch between f of x, so that the maximum value of f of x divided by g of x is like 20, then your rejection sampling algorithm is going to become quite inefficient, okay, because you're going to end up rejecting close to 95% of your values, okay? All right, so let's just look at a few pictures, and hopefully I can explain it with a little bit of intuition here, all right? So this is a histogram of the 100,000 values that I've proposed from g of x. Okay, so it's a histogram of the proposed values which come from the random exponential, and that's g of x. Okay, and it looks exactly as we would expect in that the values are exponentially distributed. Okay, values near 0 appear a lot. Values out at 6 hardly appear ever. Okay, and we get values like 2 and 2.5. Those appear sometimes, but a lot less frequently than values at 0. Okay, but we don't want exponentially distributed values. We want values that are distributed according to the folded normal distribution. So if I overlay the density of the folded normal distribution, what we see is that this, the exponential values don't quite line up, okay? And again, we see there's spots where the exponential density proposed too many values, and then there's spots where it didn't propose enough, okay? So what I'm gonna do is I'm gonna scale either this one down, the red line down so that it fits underneath, or I'm gonna scale the orange line up so it's entirely larger than the red line, okay? So either I multiply orange by m, or I divide red by m. Okay, so whatever that scaling factor 1.32 is, we're going to just kind of scale it. Okay, and so here I went ahead and I did that. Okay, and so my proposal distribution I'm going to show here in blue, and we have the target distribution in red. And now the target distribution in red is entirely underneath the proposal distribution in blue. And so I wanted to show, the way this works now. You can think of this. So I'm looking at this histogram here, and I'm going to just take this first slice. Okay, this first little interval, which goes from 0 to 0.1. Okay, so I had R draw a whole bunch of little breaks here, and so this first slice goes from 0 to 0.1. Okay, and because values are getting proposed from the exponential distribution, we can see this bar is as tall as the exponential distribution. Okay, and that's way too many compared to the folded normal. So the folded normal looks like this red line. okay? And we can see we are proposing way too many values here, okay? And so I only want to keep this proportion, okay? So if I go from 0 to 100%, I don't want to keep 100% of this bar. I only want to keep around 60-something% of this bar, okay? I only want to keep this proportion. So I only want to go from 0 to this red line. So what proportion is that? That's going to be the ratio of R, okay? So this bar spans from 0 to 1, 0.1. So I'm saying it's centered at 0.05. And so I'm going to kind of use that as like a surrogate for what the values are in this thing, okay? So I know it's technically it's different at 0 than it is at 0.1, but we're just going to say, let's use 0.05, kind of a value in between for it. So I calculate, okay, well, what's the density? For the fold to normal distribution, the density at 0.05 is around 0.8, okay? So if I go at 0.05 and I say, well, how tall is the fold to normal? Fold to normal, this is around 0.8, okay? How tall is it here, okay? The height of the blue line here is m times g, okay? M times g at 0.05. So I plug in 0.05 into g, so e to the negative 0.05, and then I multiply it by my constant m, which is 1.32. And so the height of this density is around 1.255. So this height's around 1.255. This is a height of around 0.8. And so the ratio is around 63.5%, okay? So we only want to keep around 63% of the values that get proposed between 0 and 0.1. So if the exponential distribution proposes a value between 0 and 0.1, so we only want to keep around, 63.5% of those values, okay? Because the exponential is proposing these values way too often is our issue. All right, so how do we make sure that we only keep around 63.5% of those? Okay, so the way we keep only 63.5% of those is we generate random values of u. Okay, and u will be less than probability, any value r of x with probability r of x. So here in our case, we're going to take generate a u, and u is going to be less than 0.635, with probability 0.635. That's how the random uniform works, is that you're going to end up less than some value x with probability x. So, so if u ends up being less than 0.635, we will accept it. And if u ends up being larger than that, we're going to reject the proposed value of 0.05, and we're going to repeat, and we're going to propose another value. All right, so if we look at this slice, the exponential proposes these values a lot, and we're only going to keep around 63% of them. Is that all right? Okay, and so here, let's just look at another little slice of this exponential distribution. So if you look at just this slice here, going from 1.4 to 1.5, all right, so here I have this bar or this slice centered at 1.45, okay? What we see is that, okay, the exponential distribution doesn't propose these values as often, right? Here, this bar is like, if you look at the exponential distribution, it's like 3 or 4 times taller than this bar, okay? So the exponential distribution just doesn't propose these values that often to begin with, but that's okay. But when it does propose these, okay, how many of these do we want to keep? So we look at where the red line is compared to the blue line, and we say, yeah, we want to keep like almost all of these. Sure, sometimes we'll reject some, but if we look at kind of the values that we want to keep, we want it to fit kind of at this red line versus the blue line. So let's take a look, okay? So when we calculate the density, so I'm going to just use kind of 1.45, the center of this bar, to kind of estimate my values. So the red line is around 0.278, okay? So this red line has a height of around 0.278. and the blue line has a height of around 0.309, 0.31. Okay, so if you take the ratio between these two, it says, yeah, you should keep around 90% of the values. Okay, so if a value between 1.4 and 1.5 gets proposed, we're going to keep around 90% of those values. Okay, and the exponential distribution is only going to propose these values about 1/4 as often as the values over here. Okay, so if it proposes a value between 0 and 0.1, which happens a lot, we're going to keep it with around probability 63%. If it proposes a value between 1.4 and 1.5, which happens about as quarter often as these values over here, we're going to keep it with around probability 90%. And overall, what we keep will look kind of like the target distribution. Okay, so again, we generate a value u from the uniform distribution, and we'll accept it if u is less than r of x. So why do I need u? Okay, so the reason why I need u is how do you say we should accept something with probability 90%? Okay, so this is, it's not, so I'll talk about the difference between this and important sampling. Important sampling, you're going to kind of keep every single value that gets proposed. But here, either a value gets kept or a value gets thrown away. Okay, you can't keep 90% of a value. So if I'm proposing a value like, so that let's say this distribution generates a value 1.47. Should 1.47 be in my sample? And the answer is sometimes yes and sometimes no. 90% of the time, 1.47 should be in my sample, but 10% of the time it shouldn't. Okay, every time I propose it. And so I can't just, so how do I make sure that I'm going to keep it with a probability of 0.9 or 90%? I generate a u, and if u is less than 90%, I will keep it. And if u is greater than 90%, I throw it away. Okay, and u is going to be less than 90% of the time. Okay, and so so that's how I kind of say I'm going to keep this proposed value with this probability. Okay, because either I have to keep it or I don't. And I can't, if I flip a coin, I'm only going to keep it with 50% probability. So we're going to generate a u, and we can say if it ends up less than this value, that happens 90% of the time. So I hope that makes sense. Okay, and so this is kind of a picture with a whole bunch of dots here. And so what we can see is that, okay, yeah, values between 0 and 0.1 get proposed a lot, okay? And I can count up these values, and we're going to keep around 63.5% of those. Meanwhile, values between 1.4 and 1.5, because they're coming from the exponential distribution, just don't get proposed as often. And so when I do propose a value, we're going to keep around 90% of those, okay? And I can kind of count up these values and see, okay, well, how many did I keep and how many did I throw away? And so I went ahead and just kind of did this empirically. And I said, okay, how many values did I propose that are less than 0.1, between 0 and 0.1? And it says I proposed almost 10,000, around 9,600, 9,596 values, okay? And out of those values, how many did I keep? I kept around 6,000 of them. So that's around an acceptance ratio of around 62.5, 63%, okay? And theoretically, we're supposed to keep around 63.5%. So we're getting something close empirically. And then I say, okay, well, how many values did I propose that are between 1.4 and 1.5? How many values did I propose in this region? Okay. It says, yeah, you know, you proposed only around 2,328, okay? Which, you know, is about a quarter of this. So you proposed about this many. Okay, how many did we end up keeping? We kept around 2,100 of those. And so, you know, we kept around 90%, 91% of those values, okay? Again, which aligns with kind of our acceptance ratio. And here we're just kind of looking at slices here, but, you know, when you do the actual rejection sampler, you follow this and it's, you just take whatever value it is and you don't have to worry about slicing it into tiny little things. It's, you know, you have infinitely thin slices here. And then, so, you know, values like 4.0, the exponential distribution doesn't propose these values very often to begin with. And when they do get proposed, if you look at what proportion is underneath the normal distribution curve, you know, very, very, very few. So values out here don't get proposed very often. And if they do get proposed, almost all of them get rejected anyway. Okay. All right, so hopefully that helps make sense of this. And so I've got maybe a slightly more mathematically rigorous proof to kind of show how rejection sampling works. All right. And so to kind of prove or show that rejection sampling works at a mathematical level. So, you know, we looked at pictures, which is always nice and hopefully provides a little bit of intuition, but, you know, that doesn't really work mathematically. It'd be nice. I think, I'm trying to think, there's like a handful of math proofs that were proven by just drawing pictures, but in general, it doesn't work that way. So what we need to show is that even though we're using g of x to propose random values of x, okay, what we need to show is that if we apply this acceptance probability, this ratio, r of x, to decide whether we accept it or not, that the result is going to be equivalent to f of x, okay? We want to show that even though x gets proposed from g of x, if once I apply this condition that x has to be accepted with this probability, that the result is going to be equivalent to f of x. Okay, and if we can show that the result is equivalent to f of x, then we are good. All right, so this is what that proof could look like. All right, and we're going to use Bayes' rule. Okay, so when we use Bayes' rule, you know, it's probability of a given b is b given a times the probability of a divided by the probability of b. Wait, what? Yeah. That denominator is equal to basically the sum or the integral of the numerator across all possible values of x. All right. So the numerator here, I've got the probability that x is equal to x given that x is accepted. This is equal to the probability that x is accepted given that x equals x, multiplied by probability that x equals x. Okay. And then this denominator, the probability that x is accepted, is basically the numerator evaluated across all possible values of x. Okay, so we take the numerator and we evaluate it across all possible values of x. So this is going to be the probability that we accept x, okay, given a particular value of x, is going to be, that's equal to our acceptance ratio, r of x, right? So it's the probability that some random uniform value ends up less than our ratio r of x, okay, you know, evaluated at x. And then the probability that we even propose this value of x, okay, x comes from the density g of x, right? So the numerator is going to be the probability that u is less than r of x multiplied by the density g of x, okay? And then the denominator is the numerator evaluated across all possible values of x. So we're going to take this numerator and I'm going to just integrate it, okay, across the entire domain of x, or the support of x, okay, dx. Okay, and so what do we get? Okay, well, what's the probability that u is going to be less than r of x? Well, that's going to be equal to whatever r of x is, and r of x is f of x divided by m times g of x, okay? So here I've got f of x divided by m times g of x multiplied by g of x over here. So this g of x cancels with this g of x, and I'm going to be left with f of x divided by m. Okay, in the numerator here, f of x divided by m, because these g of x cancel. All right, this integral here, okay, well, here I've got this g of x will cancel with this g of x. And then we've got the integral of f of x. Okay, f of x is a PDF. And so we know that all PDFs evaluate to 1, okay, when you integrate them, right? So if you integrate f of x across all possible values of x, we know that that's going to equal 1. So this integral is going to become 1 divided by m, and then the g of x is canceled, so we got 1 over m. So I got f of x over m divided by 1 over m, and that's going to result in f of x. Okay, and so the probability of getting a particular value x, given that we accept x in the first place, that's going to be f of x. And that's what we wanted to show. So, so that's that. And I wrote up, something happened. Okay. And I have got one last slide here for rejection sampling versus importance sampling. Okay. And oops, something happened. All right, well, I don't know what happened. Okay. Oh, here it is. Okay. So rejection sampling and importance sampling are similar, but are different, okay? Both methods deal with this problem of not being able to generate samples directly from some distribution f of x, right? And both of those problems, or both of those methods, solve the problem by sampling from a different distribution, g of x, instead of f of x. Okay, and then they compensate by using some kind of ratio of either f over g or f divided by m times g or something like that. Okay, here's the important distinction. Rejection sampling is a method to generate a random sample from some distribution f. Okay, so if you need a random sample, you use rejection sampling. Whereas importance sampling is used to estimate the expected value of a function. So, you know, we do like Monte Carlo integration and we need to, or a Monte Carlo estimation, and we need to estimate, you know, the expected value of h of x given that x comes from some distribution f. Okay, that's when we use importance sampling. Okay, so rejection sampling is for generating a sample. Importance sampling is to estimate the expected value of a function. There's similarities, but they have different kind of goals. And so, you know, I think importance sampling is not a good name, and I think it should be called weighted Monte Carlo integration, but all the textbooks call it importance sampling. That's just kind of the name that's established in the literature, but I think it's a little bit confusing because rejection sampling, I think that makes sense because sampling implies that you're trying to generate a sample, and I think that makes sense. Okay, importance sampling, this word sampling makes it feel like you're generating a sample, but you're not. You're estimating the expected value of a function. Okay, where, you know, Monte Carlo integration or Monte Carlo estimation, you're estimating the expected value of a function. And the only difference between regular Monte Carlo integration and importance sampling is that you weight the values when you do importance sampling. So I think this would be a better name, but I'm not the one in charge of naming stuff. So this is what we have. Okay. And then another important difference is that rejection sampling throws away values if it doesn't meet this kind of acceptance criteria, right? So if u comes in greater than this, you're going to just toss that value. Importance sampling doesn't throw away any values, okay? If there's a certain region where the proposal distribution proposes way too many values, rather than throwing some of them away, what importance sampling will do is it just weighs those things less, okay? It just weighs them less. And in the factor of the expected value calculation. And then question, of all the methods that we learned, only rejection sampling can be used to generate a random sample. We have a couple ways to generate random samples. Okay, we can generate random samples using rejection sampling. We can generate a random sample using inverse CDF. Okay, so you did inverse CDF and you were tested on that. You can generate a random sample using like convolutions, and we talked about convolutions a little bit last week as well, where it's like, you know, you take your normal distributed values and then you square them and stuff, and you get chi-squared values and stuff. Oh my goodness, I forgot quiz answers, and then I have like animations to show you. Have I given you any quiz answers? None. Okay, I might as well give you all three then right now. Okay, so the answers are D, B, and A. So dog, bear, apple. Okay, D as in dog, B as in bear, A as in apple. Those are the 3 letters for the quiz today. D, B, and A. Dog, bear, apple. Okay, and then, okay, so let me show you some little animations that I've made. Okay, so this first animation, yeah, I'll re-upload the PowerPoint with the extra last slide. Okay, I'll do that. This first animation is it's just going to show the exponential sampling. Okay, where you're just going to see vertical lines generated, and so what you're going to see is you're going to see a lot of lines proposed near 0, and very few lines proposed to near 3. Okay, so I'm going to just kind of play this, and this is an animation built using R. There's a package called Library Animation, and I wrote the code. I can share my code, but I'm a little embarrassed to share my code right now because it's like it's not pretty. So I'm like gonna clean it up and add comments and make it, you know, follow style guides and stuff like that. So give me give me a little time to clean up my code. Right. Okay. So anyway, what we're seeing here is that when it's done, we see a high concentration of values near 0 and a low concentration of values near 3. Okay, and it almost looks like a gradient. Okay, except it's random. Okay, and that this area, because the lines are so close, it's like dense dark, and as these values get proposed less often, it kind of becomes a gray. All right, and so here, this is going to be the rejection sampling algorithm. And I'll run through a few slides just manually here, okay? And so here it proposes this value, I don't know, whatever this is, 1.3, okay? And then it draws a random value u, okay? And so 0, if u is 0, this dot would show at the bottom. And if u is 1, it shows at the very top. The height of this line goes to the blue line, the exponential distribution. Okay, and so this line or u ends up lower than the normal PDF, and so we will accept it. Okay, and so because we accept it, it gets a green dot. All right, so we would accept that value. Next, we go to I don't know, what is this, 0.6? Okay, and we propose 0.6 as a value, and we will generate a u. Okay, and u just happens to be right at this line. Okay, I think it's just a tiny bit over it. Okay, and so when we look at this and we say, okay, well, is u above the desired density? It is. So we're going to reject this value. So this value is going to get thrown away. We're not going to keep it. Okay, we propose another value. We propose, say, like 1.8, 1.7. And we're going to generate a u between 0 and 1. Okay, and so we propose a value. The u ends up being like 0.95 or something, almost 100% at the blue line. Blue line would be 100%. So 0.95, so it's above the line, so we reject it. Okay, here's another value. We propose a value like 0.1. We generate a u. U ends up, I don't know, point something, okay, a little bit above this line, so this gets rejected. Okay, here's another value u, and we propose a value we propose a value like 0.4. The u we generate looks like to be, I don't know, 0.05 or something very small, so that's way below the curve, so we are going to accept it. Okay, and it's just, I'm going to go ahead and run it, and so it just keeps. And what you're going to notice is that values near 0 get proposed more frequently. Every now and then we will propose a value out here, but not very often. Okay, and you can see that when we propose a value, sometimes it will get accepted and sometimes it'll get rejected. Okay, and again, we're noticing more values around 0 get proposed, and values out here don't get proposed as often. And when they do, a lot of them will get rejected. Okay. So this is just kind of a little animation here of values and stuff. Okay, and so that's the rejection sampling algorithm here as a little animation, and I guess I'll post the code here. Okay, so anyway, this is the animation package, and you can create your own animations, and it's kind of fun, and I think it's kind of neat here. Okay, all right, that's all I've got for you guys today. So we'll end here, and we'll see you guys on Friday. I'll probably post a homework assignment pretty soon, so you guys have that to look forward to. All right, have a good day, and we'll see you guys on Friday.